Okay, so today we're going to do two different comparison tests. And the first one is called limit comparison. You're going to do a comparison test when the series you have is more difficult, but you can compare it to something simpler. Like the idea is you want to compare it to something that you could do relatively easily. Like you're trying to make your life easier. So you're going to try and compare it to something that you could answer really easily. So for limit comparison, both of your series have to be positive, so bigger than 0. So it's not going to work for an alternating series. I guess you compare it to something that wouldn't be alternating. Anyway, if it was an alternating series test, you would just do an alternating series test. You wouldn't even bother with a limit comparison. So anyway, those both have to be bigger than 0. And then your limit as n goes to infinity of one of them over the other. Now I wrote a over b, but you could put b over a. It actually doesn't matter. If that limit is finite, I think it needs to also be positive. Finite and positive, then either both of the series converge or they both diverge. So it's like the integral test. Like if the integral works, then the series is going to as well. It's like if the one you're comparing it to works, then the original series is going to work as well. I always struggle over how to say that in a really concise way. So if you do that limit and you get a finite positive number, both series converge or both diverge. What one does, the other one does, is the short way of saying. So if you have something that is, needlessly complicated, or none of this is going to work, like it's not geometric, it's not a p-series, it's not alternating, you couldn't do an integral, then you're going to try one of these. Okay. So let's look at the first one. So when you look at something like that, if your first thought is, wow, I hate this, you're a normal person, okay? It's not geometric, it's not telescoping, it's not alternating, it's not a p-series. You get what I'm saying? Like, do you want to do an integral of that? No. Okay, so we're going to do a comparison, and we're going to try and compare it to something that would be relatively easy to do. So we're going to compare it to another series. Now, when you compare it, it has to be relatively similar. You can't just compare it to like anything in the world. And basically what you do is you just use the variables. You get rid of any extraneous numbers. So I'm just going to leave off that +1. So come with me on this. If you go to simplify this, what is the power for a square root? That'd be 1/2. And then this is 2. So you would end up with 1 over n to the 1 and 1/2. Like if you have a 1/2 in the numerator and a 2 in the denominator, it's going to end up being 1 1/2 in the denominator. You're all still just kind of staring at me. Let me pause this and do a different example. All right, so now we have that. The reason that's easier is because it's one of these named ones. Which kind of series is that? Like I compared it to something that I can do relatively easily. That is a p-series, and p is greater than 1, so it's going to, do you see how we did that? Like we just talked our way through it without having to do any work. So we're going to say that this one converges because it's a p-series with p equals 3/2, which is bigger than 1. So that's your justification. So here's what we're trying to accomplish. Here's our goal. What we want to say is, since this one converges too. That's what we want to say. You're coming with me on that? So you're going to do this limit. It's going to look awful for a second, but then we're going to fix it. There's going to be one step where it looks completely horrible, but you kind of have to trust the process, all right? So we're going to do limit as n goes to infinity of this one over this one. So it'll be square root of n over n squared plus 1. I just copied that over 1 over n to the 3/2. Now, when you divide by a fraction, you multiply by, good. So this is going to be limit as n goes to infinity. And I'm going to keep this first part the same. And I'm just going to flip this over. So it'll be n to the 3/2 over 1. So again, this step always looks completely awful because you have a fraction over another fraction. But then you just reciprocate it. And now we're going to do the limit as n goes to infinity. All right, so let's sort through that and see what we have. This is n to the 1/2. And then this is n to the 3/2. So 1/2 plus 3/2 would be n2. That's what my algebra 1 kids are. n2. I've just learned to accept it. N squared, and then this is also n squared. So if they're the same, you use the coefficients, which aren't written, they're both 1. So this limit goes to 1. I guess you could write 1 is a positive finite number, but that's not necessary. Like, it's just assumed that everybody understands 1 is a positive finite number. And so since this one converges and this came out to a positive finite number, we're going to say converges by limit comparison. So what your goal is to say, since the one you compared it to converges, the original one converges as well. That was weird with the fractions. Okay, let's try another one. Wait, go ahead. Question? I would love to be asked a question. I'm just writing up the next one. You want to found that this converges? It only converges if this limit is positive and finite. You have to show that that limit comes out to a positive and finite number before you're allowed to conclude that they do the same thing. That's part of the process. It's kind of like with the alternating series test, how you have to do both of these things. It's kind of like that's the second step too. So you leave out any extraneous numbers when you do the comparison because you're trying to compare it to something simpler. So you sort of leave out anything that's extra. I'm going to show you because we're going to do the same thing in this one. Basically, you just keep the variables and you leave out any extra numbers. Like you're leaving out all the fluff. Okay. So did we write this one down? I didn't write down the second one. So when you look at it, you want to go, okay, it's not geometric. It's not telescoping. It's not a p-series. I don't want to integrate that. I mean, I guess you could. That one would integrate with a U substitution, but I wouldn't. I would do a comparison. And that's the lesson I'm teaching, so that's what we're going to do. So we're going to compare that to something that we're going to try and make be a whole lot simpler. Because this is complicated. I want to compare it to something that's going to be easier to deal with. So I'm going to make it be 1 over square root of n. Do you see how I just got rid of the 4 and the -2? You're allowed to do that as long as you keep all the variables. You haven't fundamentally changed it. You just left out all the parts that are complicating it. You're just paring it down to like its most basic form. 2? Yeah, it doesn't matter. As long as you keep the variables, you haven't fundamentally changed. It's kind of like comparing a quadratic to a quadratic. You can get rid of all the extra numbers around it, like the stretch or shrink or the shifts. Still a quadratic. Where, yes, exactly. Yeah. You're just getting rid of all the numbers, basically. But in its most basic form, these are still comparable. And the reason we're comparing it to this is a whole lot easier because this is one of our named ones. What kind of series is that? That's a p-series where p is 1/2. So converges or diverges. All right, so we're going to say this diverges because it's a p-series with p equals 1/2, which is less than 1. So that's your justification for that. This one diverges because it's a p-series, 1/2 is smaller than 1. So the next goal is, what we want to say is, because this one diverges, the original one diverges too. The one you're comparing it to, we want to say this one does the same thing. But the second step to it is you have to show that this limit comes out to a finite positive number. All right, so again, the first step is going to look kind of awful. because it's going to be a fraction over another fraction. But again, just trust the process. It's going to be this one, 1 over square root 4n minus 2 over the one we compared it to. So again, I realize that looks awful. But what are we going to do with the denominator? Yeah, multiply by the reciprocal. So we're going to end up flipping it over. So do you see how this is a square root of n and this is also a square root of n? When they're the same, you use the coefficients. Now in the numerator, that's a 1. In the denominator, it is a little tricky. What is technically our coefficient with this? Oh, good, good. Why is it 2? Square root of 4 is 2. And the point is 1/2 is a finite positive number. So we would say, like, our big final conclusion to the whole thing is that this series diverges by limit comparison. If this came out to a 4 instead of a 1/2, it. Oh, like if this part was incorrect, but your conclusion was correct, they'd still give you the point for this. Because you got a finite positive number. And if you did this part correct, the comparison, that does get weird. How, like, it depends on how many points they made it worth and all of that. But I feel like they would still give you that. We're just gonna do one more of these. Oh yeah, go ahead.
Why get rid of the 2?
Yeah, you just get rid of all the fluff. You just want to pare it down to its most simple, basic form. Okay, we'll do one more of these. And if you look at that and you're like, that's awful, congratulations, you're a normal person. You use a comparison test when all this other stuff's not going to work. It's kind of like, I tried everything else and I'm out of options. So let me compare it to something that's going to be a whole lot simpler. So let's find something a whole lot simpler to compare this to. Let me get everybody there. Now, look, we're going to get rid of the 4 and we're going to get rid of the +1. So I'm covering all that up. So what's still in the numerator? Okay. And then in the denominator, there's n cubed. These can simplify a little bit though. N squared will go on the bottom. So it'll be 2 to the n over n squared. Now, the previous 2 we did were p-series. We compared them to a p-series. This is not, it's also not geometric. It's not telescoping. So can you find something else on our board here that we could try for this? Because it's simpler than that one for sure, but it's still not one of the like special named ones. So we got to try something else. I would do an nth term test. If you do limit as n goes to infinity of that, the numerator is exponential. So that means it's growing super, 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 super fast, way faster than the denominator. And so what does that limit come out to? Infinity. So we can say that this one, the one we compared to, does what? Diverges by nth term test. So the goal then is to say that the original one also diverges. You just have to show that the limit comes out to a positive finite number. That's like the second part of the test. So we said this one diverges. We want to say this one diverges too. So we're going to do limit. And again, this is going to look gross for the first step. You have to trust the process. Limit is n goes to infinity of this first one. I just copied that over the one you compared it to. And so again, you're gonna flip that. And I know you're like, it doesn't look a whole lot better, but something will cancel out. Do you see anything that's gonna cancel there? Yeah, the 2 to the ends are gonna cancel. So what have you got in the numerator? N to the third. Denominator is also n to the third. So when they're the same, you use coefficients, so it'll come out to 1/4. And the point is, that is a positive finite number. So what is our grand conclusion? Diverges by limit comparison. All right, so we did limit comparison. The other one is called direct comparison. I don't like this one as much. I feel like with limit comparison, if you need to justify it, you just do a limit and it just always works and then you're good. For direct comparison, you need to worry about which series is larger or smaller than the other one to compare them directly. And I find that a little bit frustrating. But again, sometimes they force your hand on the AP exam for your response. If they say, show this by direct comparison, then you have to know how to do it, okay? So we're gonna say that A is smaller than B. So you have to worry and check about which one is smaller than the other one. So we're gonna say A is smaller than B. So if, and let me think which way I want to say this first. If B converges, then A converges. And I'm gonna give you a chance to write it, and then I just want us to talk about it and think about it, because it does make sense, and I get that. So let me point to this. If this one is the smaller one and this one is the bigger one, if the bigger one converges, do you get how the one smaller than that would have to converge too? Like if the bigger one has this leveling off behavior and heads somewhere, then the smaller one's going to have to do that as well. It's almost like it's trapped by the large one. Does this make sense? Like that's how I do it in my mind. I'm like, well, if the bigger one is going somewhere, then the smaller one is too. Then the other way around, if A diverges, then, whoops, that's a horrible sigma, then B diverges. So if the smaller one heads off towards infinity, then the bigger one is going to head off towards infinity too. Does that make sense? Like if the smaller one diverges, it makes sense. And so like I get all that. But when you actually work out a problem, you have to think through when you do a comparison, which one is the smaller one and which one is the bigger one. And that can get kind of complicated. Okay, that's why I kind of like the limit one better, because you just do a limit and it's going to work and then you're fine. Here you have to actually worry about which one is which. Okay, but let's try a couple. So you would hopefully look at that and go, it's not geometric, it's not a p-series. I don't want to integrate it. I was going to ask that. Nice job. If you did integrate it, it would be arctangent. But we're going to do a comparison test. Okay. So we're going to compare it to what? What would you want to compare it to something simpler? That's the idea. 1 over n squared. And again, when you're doing multiple choice questions, you don't have to write, like, again, I probably shouldn't record this, but you don't have to write all this. If mentally you go, hey, that's n squared, that's a p-series, like you can sort of do some of it in your head. So would this, I just told you it's a p-series. I think you knew that though. Is it going to converge or diverge? So it converges because p-series with p equals 2, which is bigger than 1. So here's the goal. We want to say, because that one converges, the other one converges as well. But we have to prove that this is the bigger one and this is the smaller one. If the bigger one converges, then the smaller one does too. So we have to show that this is bigger than this. That's what we have to do. Okay, so I usually write it out the way that I want it to go and then just see if it makes sense. Is this 1 over n squared plus 4 gonna be smaller than 1 over n squared? Like, is that true? Yes, because the one with the bigger denominator is the smaller fraction. Okay, so that's what I usually do. I usually write it the way I want it to go, and then I check if that is true or not. So this is true for n's bigger than 1. And so then your grand conclusion is what? Yep, so we would say converges by direct comparison. That went smoothly. I think I got you guys like all warmed up here finally. Okay, I'm gonna do 3 of each of these. So we're just gonna do 2 more. So you would hopefully go, hey, that's a mess. So let's compare it to something simpler. So we're going to compare it to 1 over 3 to the n. I'm actually going to write that a little differently so that we can see it better. And if you can do that in your head, you don't need to rewrite it, but I would rewrite it as 1/3 to the n, because then it makes it easier to identify which one of these this is. So what type of series is that? Geometric. And if you even want to put a 1 in here to see that it's 1 times 1/3 to the n. So r is 1/3. What does that mean? Converges. So we're going to say this one converges because geometric with absolute value of r equals 1/3, which is smaller than 1. And sorry, I ran into the hole in the paper. Go ahead.
So I didn't realize it was geometric, but I think convergence.
So the nth term test can never tell you that something converges. It can only tell you, that's the annoying thing about that test. It can only tell you that it diverges. The other option is a no conclusion. So you can, and we did use an nth term test to show diverges, but you can't ever use that to show converges, which is a little frustrating. Yeah, go ahead.
How did you get the 1 over 3?
I mean, that's what it is. I mean, this is 1 to the n, and that's 3 to the n, so it's 1/3 to the n. Like, just algebraically, that's true. Yeah, like, sorry, that's a totally crap answer, but yeah, because math, like, that's it just is. Sorry. Okay, so here's what we want to do. This is our goal. We want to say, because this one converges, this one does too. But in order for that to be the case, we need to show that this is the bigger one. If the bigger one converges, then the smaller one also converges. So we need to show this is smaller than this. So again, I usually just write it out the way that I want it to be true and then see if that's true. It's like wishful thinking. Like, I write it out the way I want it to happen, and then I just check and see if that makes sense. So is this statement true? Yes, because the one with the bigger denominator is the smaller fraction. So since that's true, what's our grand conclusion to the whole thing? Converges by direct comparison. And we'll just do one more. And again, the whole idea of comparing is you want to compare it to something simpler. Like, you're taking something that was complicated and trying to compare it to something that's a lot easier to manage. All right, so what would we compare this one to? Yep, 1 over square root of n. Getting rid of all the fluff. You're comparing it. I like that idea. Oh, I erased it. Of like comparing to a quote unquote parent function. Like, get rid of everything that's been transformed. So what do we know about this one? Again, the point of doing that is you compared it to something easier. P series, so it's going to diverge. So diverges because P series with P equals 1/2, which is smaller than 1. So here's the goal. We want to say, as a heads up, you're not going to like this. And this is why I don't really like this test much either. That's why if I have to do one, I do a limit comparison. We want to say since this one diverges, this one does too. But in order for that to be the case, that has to be the smaller one. If the smaller one diverges, then the bigger one does too. So we have to show that this is smaller than this. So I usually write it out the way that I want it to go, and then I see if that's true or not. And what? That's not true, which means we are totally back to the drawing board. And that's why I don't like this one as much. Because if it didn't work, we just did all of that and we have to totally start over. It's like, just take it and crumple it and throw it away. You got to start it. So let's try and compare to something different. And here's where I don't, again, I shouldn't be letting my editorial comments in here, but this is why I don't like this that much. Since the 1/square root of n didn't work, we're going to compare it to just 1/n. And that does feel a little bit wrong to me, but we had to try something else. And that worked, because see, I feel like we strayed away from the parent function, but you are allowed to do this as long as you justify. Now that's also a P series, and it would do what? So it's diverges because P series with P equals what? 1, which is less than or equal to 1. And I don't know if you remember this, but that's called the harmonic series, the 1/n. Because they sometimes throw that vocabulary word at you. If they say the harmonic series, it's 1/n. It's a P series where P is 1. So again, the goal is we want to say since this one diverges, this one does too. But that means that that has to be the smaller one. The smaller one diverges, the bigger one diverges. So I need to say this is smaller than the original one. And so again, I always write it out the way that I want it to be true and then see if that's true. And so would that be true? It would be true eventually. It's not going to be true for n greater than or equal to 1. Because look, if you plug in 1, what would you get? You would have 1 smaller than 1 smaller than, not a half, but a third, which isn't true. But eventually it's going to catch up. I think it's at 4 or 5. Let's try 4. If you plug in 4, this would be a 4th, and this would be, I picked 4 because it's a perfect square. Okay, there we go. So it would be true for 4 and above. And again, as long as it's like eventually true, then you can do your conclusion. So what's the whole conclusion to the whole thing? The original series does what? Diverges by direct comparison. And once again, that's why if I get a choice, I would do a limit comparison because you don't have to worry about which one is bigger and which one is